Hello and welcome. This is a demonstration of our software QPMoptics, your tool for simulation and optimization of photon pair creation by parametric down conversion in periodically poled crystals. QPMoptics not only analyzes the setup that you enter, it also suggests in which way it can be improved for the sake of optimal quantum performance and efficiency. The software comes with a graphical user interface which allows for an intuitive use that doesn't require much of an introduction. Basically, all you need to do is to enter your experimental setup, select the plots that you want to be displayed, and click the Go button. Your plots will pop up within a few seconds and your numerical results will be displayed in the results panel. But let's go into a bit more detail to get you familiar with QPMoptics and the features it offers to you. Enter the wavelengths of your pump and signal radiation. If you're going for frequency to generate SPDC, you might like to use the designated checkbox. Select the polarization directions of pump, signal and idler. The spectrum of the pump laser is by default assumed to be Gaussian. Alternatively, the user can customize the pump spectrum by entering an arbitrary analytic expression that describes their laser system best. Enter the full width at half maximum, the Gaussian bandwidth, or the pulse duration of your laser. You can select between three different periodically poled crystals: potassium titanyl phosphate, lithium niobate and lithium tantalate. By the way, you can use the preview function to promptly get an idea of how a change of your parameters affects your experiment. Just press the preview button and get a first glimpse on how the joint spectral intensity distribution will look like. Specify either the temperature that you want to operate at and let the program compute the required periodicity of your nonlinear crystal. Or alternatively, the other way round. To conclude with the input of your experimental setup, select the QPM order. Now, let QPMoptics know what you would like it to compute. The calculation of signal and idler spectra as well as the optimization of the spectral purity are more time-consuming and can be opted out if not required. Now select the plots that you would like to see. Figure 1 shows you the joint spectral intensity distribution in addition to the pump and QPM envelope intensities. Figures 2a and 2b depict the spectral quantum purity with respect to crystal length, pulse duration and bandwidth. Figure 3 contains various plots related to phase matching. Among others, you get to see your tolerances in crystal periodicity and temperature, a temperature tuning curve and an illustration of how signal and idler wavelengths deviate with varying temperature. Figure 4 displays the spectral distributions of pump, signal and idler. Figure 5 gives you additional perspectives on the joint spectral intensity distribution. You can choose in which way you want your plots to be printed, collected in a figure, or one by one for convenient further use in your publication. Now specify the range that you would like to have investigated and decide for a resolution. A higher resolution will deliver more accurate results but consume a bit more computation time. When everything is entered successfully, press the Go button and let QPMoptics do its work. In the results panel you get to see phase matching periodicity and temperature, the QPM order, and the accessed component of the material's nonlinearity tensor. You get the group delays of pump, signal and idler as well as their relative group delays with respect to each other and their maximal relative time delay. The software also computes bandwidth and coherence time of your output radiation. Moreover, QPMoptics displays important quantum parameters, the Schmidt number, quantum purity and the expected Hong-Ou-Mandel visibility. Spectral correlations between your signal and idler radiation will lead to a low purity of your generated quantum states. However, QPMoptics suggests you in which way to adapt your experiment for the sake of high quantum performance. It will display the optimal crystal length for your laser, or the optimal laser spectrum to match with your nonlinear crystal. Following the suggestions of QPMoptics, you are able to find the ideal experimental setup in a matter of minutes. Thank you.